Okay. So, now we talk about modulation bandwidth. Now, we start with the rate equation, what is called as a rate equation. Now, a part of this rate equation, so rate equation tells you the rate at which the carrier density changes as a function of time, rate of decay of carrier density or rate of growth of carrier density, right, rate of change of carrier density, which means change in carrier density divided by time. So, what are the processes happening in a semiconductor actually? You have a forward biased junction, so you are injecting carriers. So, the rate at which you are injecting is decided by your current, right, and we use this concept to find out what is a power, right. We said I divided by Q is the rate at which you are injecting the carriers. So, that is the same as this I divided by Q, instead of I it is written as J, that J is in current density. So, this term is the same as I by Q. This carrier density, remember, it is number of carriers per unit volume, which is why when you write it in this form, J is current density in area per ampere per meter square, and there is a thickness which will give you the volume element. So, this is the rate of injection. So, the carrier is getting, the number of carriers are increasing because you are injecting carriers into the system, and they are recombining, and so the number of carriers will get reduced from the system, and the rate of recombination, we already said there is a radiative recombination, there is a non-radiative recombination. So, your radiative recombination plus the non-radiative recombination needs to be considered. So, you need to consider n by tau, where the tau now represents both radiative and non-radiative recombination. That is just written in terms of current. So, this is I by Q minus n by C. Why are we interested in writing this equation as a function of time now? I mean, rate, we are writing as rate and not a steady state condition. What would be a steady state condition? Let us say you are giving a fixed DC current into the semiconductor, and you assume that the steady state has reached. Under steady state condition, you will say dN by dt should be 0. There is no dynamics in the system. So, when dN by dt is 0, under steady state, you have I by Q is equal to n by tau C, or I by Q is equal to J by QD. So, the steady state carrier density is J times tau C by QD. When you are modulating, what are you doing? So, what is the difference in terms of power versus Li curve? This is the Li curve. When we say steady state, what we mean is that we are operating at a specific current, and when that operation is on, there are no changes, the LED is not fluctuating, it is not giving different powers, which means this dN by dt must be 0. The rate at which it gets generated must be the same as the rate at which the electron and the holes are recombining. When that is happening, you have n is equal to J tau C by QD. But when you are modulating, that is not what is happening. Let us say you are doing an intensity modulation. You are making the current, you want to have on off keying, you want to have high power and low power. So, what should you do? To get high power and a low power, what you can do is, you can say that this is my bias current about which I can increase the current and decrease the current about this bias current. So, when you are increasing the current to, let us say, a maximum value, the power is largest. When you are decreasing the current to a minimum value, the power is the least. And if you want to completely turn it off, what should you do? You should not do like this. You should actually make sure that the low is actually going to 0. This is 0 current, so that you get the largest extinction. This is how you would do a modulation to get on off keyed output. But the question is, how fast can you modulate? What should be the largest repetition rate that you can get in the system? What is the largest data rate that can be supported in the system? So, to do that analysis, you typically do not use a square wave, you use a harmonic analysis. And what's the meaning of harmonic analysis? You look at the response of the system at specific frequencies, and then you say that what is the frequency at which the response drops by, let's say, 50%. That gives you the modulation depth. So, the question is, we are using tau c. Now, tau c, if you remember, is constituted by a generation as well as recombination. 1 over tau c was 1 by tau r plus 1 by tau nr, right. So, here when you write the rate equation, you do not care whether it goes into radiative or non-radiative recombination. You have to make sure that all the photons, all the electrons or all the carriers are accounted for, right. So, when you inject a certain number of carriers per time, they are either undergoing radiative or undergoing non-radiative transition. So, this actually includes both, it is not either or, okay. But as a result of the process, the fraction of power that is available at that time, we will consider the radiative part only. But as far as the rate equation is concerned, we have to consider we have to account for each carrier pair that I have generated, okay. So, as far as modulation is concerned, we have to now analyze this system to find the modulation response, we have to analyze for different frequencies. And then I can say that, okay, a square wave would mean that certain number of frequencies are supported. So, in order to support a square wave of repetition rate 1 kilobits per second, in the frequency domain I need a certain bandwidth, and whether that bandwidth can be supported or not, okay. And the model we will say is that, let us say input to the system is, which is input current, because that is the input to this transducer. I is I bias, the DC value, plus IM, and I am not going to take square wave, I am going to do a harmonic analysis. So, let us say I am exciting the system with a sinusoid of frequency omega m, okay, and I want to know what is the response of the system. So, when I change the current to the system, what is the consequence? What is the next immediate consequence? Instead of giving a fixed current, I am giving a varying current whose frequency is omega m. Now, omega m is your modulating frequency, and your objective is to find out how high can this modulation be. So, what is the immediate consequence? You change the current, you made the current oscillatory. How would the system respond? Final end goal is to change the intensity by the same response. But what is the immediate response of the system? If I change the current, how does the sequence of operation work? I put a current, I generate carrier density. So, if my current is sinusoidal, what happens to my carrier density? That is supposed to respond to this current, which means that my carrier density, let us say response as n is equal to nb plus nm e power j omega mt. The question we are asking ourselves is the carrier density responding at the same rate as that of my incident current, or is there a sluggishness in the response? That is what we are trying to find by finding the modulation bandwidth. So, how do you find that? All what you need to do is substitute this and this in this equation, right. So, let us rewrite this equation. dN by dt was I by q minus n by tau c, and we said that I have my I as IB plus Im e power j omega mt, and the corresponding n I am assuming that it is equal to NB plus NM e power j omega mt. I am assuming that it is giving the similar response. And once I have the carrier responding this way, obviously the photons emitted will have the same response. Okay. So, we can restrict our attention to the carrier response. We say that the photon response is going to mimic the carrier density response. And if I substitute this, what happens when you say dN by dt of this? This is a constant, that is a bias current, so there is no derivative. You have Nm Jn omega mt, and the benefit of harmonic analysis in the complex exponential is derivatives become multipliers. So, this becomes j omega m Nm is equal to Ib plus Im e power j omega t, both gets divided by q minus Nb by tau c minus Nm e power j omega t by tau c. I have just substituted this. Now, the steady state values, when do you get steady state? You get steady state when you force omega to 0, that is when you get steady state. So, at steady state you know that NB is equal to, this goes to 0, this goes to 0, this goes to 0. So, all what you would get, there is no modulation. So, Im is 0, this is 0, you get back your steady state carrier density, which is Ib tau c divided by q. The suffix b just indicates that it is the bias steady state value. And if I equate the terms on each side which has omega m, or I can say that because NB is equal to Ib tau c by q, right, this term and this term will actually cancel because that is the steady state value. What I would end up is j omega m Nm is equal to Im by q. Well, I missed a e power j omega mt here. So, when you do a differentiation, you will have an e power j omega mt. Minus Nm by tau c, both multiplied by, which means that in the phasor I can now equate the amplitudes because the phasor on either side is e power j omega mt. So, I can say that j omega m Nm is equal to Im by q minus Nm by tau c. What is our objective? We want to know whether Nm is following, the carrier density is following my input modulation. So, you would say I will try to solve for Nm. Nm is equal to Nm times j omega m plus 1 by tau c is equal to Im divided by q. Therefore, your Nm is equal to Im by q divided by 1 j omega m plus 1 by tau c. What is the physical interpretation of what we are doing? So, that is what we need to do next. What is our objective now? We are not really interested in, so Nm is actually the amplitude of the modulation in carrier density. What do we want to do now? We want to find out the response of the system, and we basically want to say that this is my input, this is my system, and I have a certain output. Input is this, the output is this, right? And how do I find the response of the system? The response of the system is, you basically want h of j omega of the system. And how do you find the h of j omega of the system? You take the ratio of the Fourier equivalent or the Fourier representation of the output by Fourier representation of the input. But here there is a slight change, is that if you want to find the frequency response of Nm. So, what you want to do is, your h of j omega is what you are trying to find out, the frequency response of the system. I can say that this is nothing but your Nm in the presence of omega divided by, or n in the presence of omega divided by Nm with 0 frequency, right. When you are exciting the system with a frequency, what is my Nm, versus if I do not excite the system with a frequency, what is my Nm. And when I excite my system with the frequency, my Nm we just derived, what was that? Im by Q divided by j omega m plus 1 over tau c divided by what is Nm0? Nm0 is the steady state population density. So, that is Im by Q, again we have it here, Im by Q into tau c. Do not worry about this Im representation, I is a steady state current now. So, this is actually Ib by Q times tau c, because when the frequency is 0, the carrier density is the steady state carrier density. So, I can cancel out my Ib by Q, what I get is 1 by 1 plus j omega m tau c. I can still give a physical interpretation to this. Now, this is the transfer function of my system. If I want to actually find out what is the 3 dB bandwidth, what I should do, I mean this is a complex number, I should not deal with complex numbers. So, what I would do is I look at what is the magnitude of this complex number, and that is nothing but square root of 1 plus omega square tau square, and this tells you the response of my carrier density at a frequency omega versus the response of the carrier density at 0 frequency, and that is my modulation response. Okay. So, how do I now, so this is omega m, how do I now try to plot this? As I increase my, now what should be my y axis? Y axis is of course h of j omega, but what does this h of j omega actually represent? It represents the response of your carrier density, and we assume that an electron hole recombination is instantaneous process. So, we are assuming that the photons are also generating at the same with the same response. So, this is the response of my output power also. So, this mod h of j omega is not just the response of my carrier density, it is the same as the response of my output photons. And my x axis is omega m, that is a variable, I can keep changing my modulating frequency. I know that now when omega m is equal to 0, there is a certain response, and if I normalize with respect to that response, the response is, what does this function look like? This looks like a transfer function of a low pass filter. So, this is like a low pass filter response. So, you get something like this, and what is the omega m for which mod h of j omega is equal to now half, that is your full width at half maximum, that would correspond to 1/4 is equal to 1 by 1 plus omega m square tau c square. So, you get omega m square tau c square is equal to 3. So, that gives you a tau c of root 3 divided by, sorry, that will give you a omega m, this corresponds to 3 dB bandwidth or full width at half maximum, right. So, root 3 by tau c or Fm at full width at half maximum is root 3 by 2 pi tau c. So, at root 3 divided by 2 pi tau c, efficiency dropped by, the transfer function dropped by 50%. The question is, so what finally decides the modulation bandwidth now? It is the recombination time, and it is not just the radiative recombination time, it is the radiative plus the non-radiative recombination time. Larger the time, smaller is your bandwidth. It is like saying that the recombination itself is taking a lot of time. So, my carrier density cannot respond as fast as my input modulation speed, and so the response drops. Alright. Now, there are a couple of small things here. Is this This is what is called as optical bandwidth. Why do we call it optical bandwidth? Because we have represented the response function for carrier density, and the carrier density is proportional to the number of photons. So, this is like optical bandwidth. Y axis can represent optical power. Now, there is something called as electrical bandwidth, which we will discuss later.